This slide introduces small sample analysis, including grain size distribution, mineral analysis, X-ray and SEM analysis, and biological dating or association. These techniques provide focused information from small pieces of core or cuttings. Grain size distribution helps quantify texture. Mineral analysis helps determine composition. X-ray and SEM imaging help reveal mineralogy and pore-scale textures. Biostratigraphic information can support age and depositional environment interpretation. So while these samples may be small physically, the information they provide can be highly specialized and very important. This is another visual slide related to small samples. Your narration can highlight how these techniques allow zooming into the reservoir from a different perspective. For example, SEM can reveal clays, pore-filling cements, dissolution features, and very fine pore systems that are not easily visible in hand specimen. This is especially useful in unconventional or tight formations, where very fine-scale features control fluid storage and flow. This slide continues the same idea. I would reinforce that small sample work complements slabbed core in thin sections. One gives the macroscopic view, another gives microscopic texture, and another gives detailed mineralogical or geochemical information. Together, these methods help build a multi-scale reservoir description rather than relying on a single test. Here, biostratigraphic information can support age and depositional environment interpretation. So while these samples may be small physically, the information they provide can be highly specialized and very important. Now the deck shifts toward routine core analysis, or RCA. This is where we begin measuring standard quantitative properties such as porosity, permeability, grain density, and as-received saturation. This is a major transition in the lecture because we move from descriptive geology to laboratory petrophysics. These are the measurements most commonly used in reservoir evaluation and log calibration. This slide shows the RCA workflow, cleaning and drying, then measuring porosity, grain density, permeability, Dean-Stark saturation, gas permeability, and Klinkenberg permeability. The key teaching point here is that routine core analysis is standardized and repeatable. These measurements convert rock samples into engineering parameters that can be used in volumetric calculations, flow estimation, and reservoir models. This is the point where geology becomes strongly quantitative. This slide is an invitation to connect measurements with engineering decisions. Porosity tells us about storage. Permeability tells us about deliverability. Grain density helps with rock typing and log interpretation. Saturation helps determine hydrocarbon volume. So the lab numbers are not just academic. They directly affect estimates of reserves, predictions of fluid flow, decisions about completion intervals, and even whether a reservoir is commercial. This slide shows an actual RCA data table with depth, horizontal and vertical permeability, porosity, saturation, grain density, and lithological description. This is excellent because it demonstrates the kind of real data engineers work with when presenting this slide. Explain that core data are interval specific and often variable with depth. Some intervals have high permeability, others are tight. Some show anisotropy between horizontal and vertical permeability. Some have different saturation conditions. This variability is exactly why detailed reservoir characterization is necessary. Real reservoirs are heterogeneous.